What I want to do here is, I don't know how much it's got relevance, but nothing like this really comes up. But it's totally got relevance for this whole quantum side of things, because this is where quantum physics started. Max Planck, a very famous physicist, German, was investigating, I don't know, radiation from light bulbs or something like that. It's a very important thing. And they really wanted to understand it. They thought they had physics all sorted at the end of the 19th century, and they didn't really expect relativity or quantum physics to come along. Just like right now, we sort of don't know really where things are going, and there are probably big changes coming up. But anyway, what I've drawn here, probably in a fairly crappy way, is the black body curve, if you like. The black body is something which you expect to get, when you heat up a black object. It's a perfect emitter, perfect absorber. If you were to sample the radiation like an insider, I think the usual example they give is like a black ball that's been heated up, and on the inside a black metal, if you like, and on the inside you sample the radiation without disturbing anything, you'd be able to see black body radiation, which should have all the wavelengths, and you get this sort of curve depending on the heat. So this is wavelength and this is intensity, and this peak here is going to happen at a certain wavelength, and as you change the temperatures, so this could be for a certain temperature, and as you change the temperatures, the peak changes. So the peak actually gets to a smaller and smaller wavelength as the temperature goes up. So I don't know, we could call this one at 2000 Ks, and we could call this one at 4000 Ks. Very hot. And that peak is very characteristic of the temperature. And the peak meaning you are getting these other wavelengths being emitted at that temperature, but there's a peak. And so if we're looking for visible light, I think we would need, I don't know, about 500 degrees or something like that. And then things start to glow, right? At our temperature, 37 degrees Celsius, or about 300 and whatever it is, degrees Kelvin, we don't glow, but we glow in the infrared. And I think we glow at about 10 microns, or 10 micrometers, which is infrared. That would be where our peak is. That would be our wavelength on our graph, which is quite a big wavelength, so it's way down here somewhere. And you get a law here. We get this law called Wien's, or Wien's, I don't know how to say it, law, which relates that wavelength max. And it comes up with this number, 0.02898 times 10 to the minus 2 or something, over the temperature in Kelvin. Very nice, simple formula. So I think if we plug in our numbers, we get, what was it, 9.6 times 10 to the minus 6, something like that, for the 10 micrometers. It's really nice. But these numbers mean something, and Planck was trying to figure out what's the reality of all this. What does it really mean? So he tried to come up with a formula, and he did this all just by trial and error, just keep playing around until you come up with a formula that's going to fit these curves. Because when you did it normally, when you did it in a way which, classically, if you like, where you think that all energy levels and everything else like that can exist, then you end up with this curve that ends up sort of looking like this. You can't make it do the curve. That's what classic theory predicts. Classic prediction. This is what we measure, but the classic theory predicts that. Alright? Now, it's called the ultraviolet catastrophe, ultraviolet being the small wavelengths as we get down here. Ultraviolet catastrophe. And so it didn't work, theoretically. So Planck was trying to come up with something. So he ended up coming up with this formula, wavelength and temperature. And this is a very famous formula. And it incorporates something called Planck's constant. So 2 pi h Planck's constant, speed of light, squared, wavelength to the power of 5, e, hc, Planck's constant, speed of light, over wavelength kb, that's Boltzmann's constant, minus 1. So this formula worked. And Boltzmann constant is that one little guy there that we did. Boltzmann, very famous. This whole entropy thing. 1.38 times 10 to the minus 23. And so we end up with this new constant, Planck's constant, which gave the correct curve. The only thing is, this means that the energy was coming in discrete packets. Very, very small discreteness, because Planck's constant is very, very, very small number, right? So if Planck's constant's that really, really small number, which is 6.626 times 10 to the minus 34, really small number. But basically, what Planck was saying was that the oscillators in the black body's wall couldn't put out all the different wavelengths. They could just put them out in these discrete units. And these discrete units, this is what the quantum is all about, these packets of energy. And the discreteness was at this level. It's kind of like figuring out the digital sort of timing of the whole thing, of how this whole space-time energy thing works, and he'd figured it out. So for me, this constant is the most important one. He didn't really think that it, I think, was the way it was. I think he just thought this worked, and that was enough.